Hello, and welcome to our next presentation. This is day 3 of the final day of the symposium. And on behalf of the MIT CDOIQ Virtual Symposium, we would like to thank all our sponsors who have sponsored the symposium this year. Please keep a lookout for a very special survey that we'll be sending out shortly. In the meantime, let me thank our sponsors, Deloitte Informatica, Privacy Analytics, DAWIX, Fusion Alliance, KPMG, Santel Consultants, Tamer, Aviation, Ali Data, Big ID, Boomi, Caserta, Citizen, Data Kitchen, Garage, Okira, Pilog, Click, ThoughtSpot, Eckerson, Global ID, Snowflake, and Starburst. Please take a chance to go to Content Hub, see what content they have, download that, and if you get a chance, reach out to our partners. Without our partners, we would not be able to hold a symposium. Thank you, and we look forward to seeing you in 2021.
Hi, I'm Peter Anley, and I'm facilitating the A track today. Very pleased to welcome this morning Dinakar Deshmukh, who is the Vice President of Data Science and Analytics at GE Aviation. Folks, feel free to ask questions, and we're going to have a time slot at the end to answer those. Dinakar, please take it from here. Welcome.
Thank you, Peter. Again, thank you, MIT CDOIQ, for providing this opportunity for all of us to get together and share our experiences and what we are learning across this exciting emerging technology space. And my personal thanks to all of you for providing me an opportunity to do this. Good morning, everyone. Again, in this next 30 to 40 minutes, I'm going to share some of our experience from GE Aviation perspective on how we are using artificial intelligence and machine learning based asset health monitoring, especially how we are advancing the state of the art by external data sources. And before I go deep into my presentation, I just want to give a very brief view about whom we are and what we do. GE Aviation is a part of a GE conglomerate. Our specialization is making jet engines. We make both commercial as well as military engines. I'm very proud to say that at any given point of time in the commercial space, for every 2 seconds, there is a flight somewhere in the world taking off, which is powered by our GE partner-powered engine. So as we speak, of course, some of this information, as all of you can imagine, the COVID has changed the statistics a little bit, but we all firmly believe that COVID is not going to stay long, and we are going to return to our normal operations in every part of the world and industry to somewhat what we think is normal in some time near future. So these numbers which I'm showing here are the ones where we are operating in a normal world. So in that context, there could have been at least 2,200 aircraft in flight, flying anywhere between 50 to 500 passengers. That means that somewhere close to 300,000 passengers are relying on the technology which is being powered by GE Aviation. Now, something which is very interesting in the space where, especially the aviation, and it makes it very interesting for the engines area, is we have close to around 35,000 installed engines, and it is operating in a world of variation. Like somebody might be taking off from a very hot desert area, like 100 degree Fahrenheit, and somebody might be taking off in an area which is extremely cold, say 30 degree Fahrenheit. These operations are all over the world, and they are operating in a place which is varying significantly. Now, what is the problem which we are trying to solve, especially in the asset health monitoring side, by using artificial intelligence? The simple question the customers are asking us is, they need to have an advance notice for a potential asset problem. Also, this is a typical industry problem, which many of you might have seen and also are trying to solve this. So what is the solution for this? We all know that predictive maintenance is a solution for this. Of course, predictive maintenance has been in operation for quite some time, but what is changing in in today's world is the way how some of the contemporary technologies like machine learning / artificial intelligence is powering predictive maintenance compared to what used to be a more soft cycle based maintenance is changing a lot. Now, why it is different in aviation industry? For example, like predictive maintenance apply to any other industrial asset, how that problem becomes different when it comes to aviation. The way how all the aviation / jet engines are being designed is they have extremely low failures, and by design, because it's related to safety, so you don't have failures happening in operation, so you have very limited failures. So this makes this problems class imbalance problem. What I mean by class imbalance is, for a amount of safe operations, the occurrence of a failure or an event is in single digit. So it makes it extremely difficult when you want to build some of the predictive maintenance models by using techniques like machine learning. Now, especially when that problem becomes such difficult, now you have to look at every source of information or data available to understand what is happening. Especially in this case, what I'm showing you is, as I articulated earlier, our asset gets operated all over the world in a spectrum of varying conditions. Especially in this case, I'm showing you the way how environment gets varied across the world. So as you can see, there is a very good amount of a spectrum of environmental behavior across the globe. And especially if you want to go and build machine learning based predictive models for jet engines, you need to clearly understand where this asset is being operated, because this environmental data becomes an important factor in building predictive models which are class imbalance in nature.
Sir, this is Barry. I'm the technician. Your signal is a little bit low, and so we're losing your audio. So what I'm going to do is I'm just going to turn off your camera so we only see your slides. But you can still just continue to present, but I just wanted to alert you. And then if you could sit nice and close to your computer would be great.
Sure.
Thank you.
Now I want to show a few examples as a part of this conversation. And what you see here is a component inside a jet engine. And as you can see, it is fairly distressed. And these are the type of failures which we are potentially seeing in our assets. The key here is we don't see these problems happening on all our assets. It is happening in few assets with few operators. So that's a problem. This is another example where with a particular customer, this particular customer has huge fleet. However, there are few aircrafts which are getting corroded at a much different rate compared to the rest of the aircrafts. So this is a problem which we need to solve. And this is a picture which is taken by a borescope inside an engine. So what you see is one of the component here got bent during the operation. So it's curled. So these are the type of the problems which we are trying to solve. And these problems don't happen quite frequently, as I said. Now, so we need to understand what is happening, and a quick recap of different ways of understanding variation. One, there could be a source of variation coming through just manufacturing side of it. So manufacturing is something which you already have in-house. So you know what asset is having what components, and you also have the manufacturing details about that particular part. So you understand that manufacturing variation. It's important to bring that. Then the asset is also getting operated in a totally different in different conditions. For example, asset could be operating anywhere from 65,000 of thrust to 85,000 of thrust. It might be taking off from, say, a 30 degree Fahrenheit to 90 degree Fahrenheit. The asset could be making a travel from point A to point B which is a small duration, could be 2 hours, or the same asset could be making a point A to point B, which is an extremely long flight like 9.5 hours. In this case, these are operational stuff which is coming from the way how the customer is using your asset. And the last one, which is very important, which I have shown earlier, is the way how environment data or environment conditions are varying as a function of time, as a function of geographical position. So these are the 3 sources of data which becomes extremely important to understand this variation. Now, if we do not bring the external data source, say environment, then what you have access to is manufacturing data, because that is something which you have within your own control. The operational, because customer is operating the way how they want to operate and they will share that information. If I use only those 2 data sources, yes, I will be able to build machine learning models, but at the same time, I may not be able to build to the fidelity at which these models can be put in production. Now, one quick point I want to make. This is a typical example. There may be problems which you may be able to solve by using limited data sources. This is a kind of like a gambit of data sources which you potentially may be using. So given a problem nature, either all these data sources or a subset of this could be potentially helping to fix your problem. Now, I want to take each one of those examples and take you through how we are able to build these machine learning based models by using those data sources. As I said earlier, this particular component which was failing in operation, it was not happening for all the operators. It was happening for a specific operator operating from a specific region of the world. So what we try to do is we try to combine those 3 data sources and try to build what I call them as a machine learning based digital twin. So what you see, each dot on the animation is an asset, and we build model where it tracks the amount of distress which this part is undergoing as a function of time. And as you can clearly see, now when we combine the environmental data and some of the operational data together and feed that as an input to this machine learning model, you can clearly put a model in production which can clearly predict what is going to happen, and also importantly understand why a particular asset is behaving the way how it is behaving. Now this was very, very important because for this particular problem, we had a AD, which is like a airworthy directiveness from FAA, to have a very frequent inspections for customers who are operating this type of platform from GE. So it was a huge burden on customer. However, with the help of this type of digital AI-based predictive models, we are able to go and have this method as an alternate method of a compliance for a physical inspection. So this is a approved method by FAA for this particular problem. Now the second example which I was quoting earlier was where there is an operator where he is operating huge fleet of assets. At the same time, what is happening is all the assets were not getting corroded at the same way, and some of the assets were getting corroded more at a rapid rate than others. So we were trying to understand why it is happening. And the key here lies is, again, in this case, operations coupled with the environmental data. There is no manufacturing data here. So the way how it was solved was this operator parks this aircraft overnight in a hangar or in wherever they're actually making a point A to point B. Now, understanding that point A to point B to point C, where it is getting parked overnight, and linking that to the sea salt concentration of that particular city, and making a predictive model by combining these data sources together, we were able to clearly show what is the probability of a particular asset having a corrosion or not having a corrosion. Again, here the key is, if I did not have access to the external data which is coming from a weather perspective, especially on the sea salt content, we could have not got to a model which is as high fidelity as this one. The third example, which I was quoting earlier, was there's a particular component inside engine which is getting bent or curled. It's extremely interesting problem. Now, before I go to the this problem, I want you to understand what is ITCZ. ITCZ is intertropical convergence zone. Basically, when the air from north hemisphere and when the air from southern hemisphere will travel together towards equator, and around like a 25,000 feet altitude, it forms what we call the ice crystal zone. So it is not going to be constant. It varies across the time zone. So what you see here for the July time piece, this is how it looks like, and for the January, the ITCZ band looks like. Now, why it is important in this case? I'm just showing one sample flight. So in this case, this is going from point A to point B. And as you can see, as the aircraft is passing through the intertropical convergence zone, which is ice crystals, these are actually entering into jet engine and actually bending high pressure compressor blade tip. Now, when we combined the routes of the way how the aircraft is being flown, coupled that with what is the typical ITCZ zone for that particular day and for the particular month, you combine both of them and you build models by using that. Then you suddenly start building your cumulative models by using machine learning, which can potentially tell you what is the potential risk of that asset should be having this kind of problem. Again, in this case, the key was using a source which is coming from external sources like weather and coupling that with the operations and applying technology on top of it and building a predictive model for that. Now, whatever I have discussed till now, those are the three examples. And as I said, every problem necessarily does not need all of them to solve the problem. At the same time, these are some of the examples where external data sources like the weather or ITCZ has become very important for us to solve some of the problems which we were facing in our area. At the same time, I want to just bring back all of you. How do we make this happen? For example, like what is the technology? How we approach this entire problem? So we, especially within GE Aviation, around 12 years back, we brought in the concept of data lake. Especially earlier, we used to have all the data collected in a structured way in the form of data warehouses. But especially when you're trying to link multiple data sources together, you need to have a data lake approach to solve your problem. And we exactly approached what other industries were doing in this space. So basically, we expanded the amount of data which we're collecting, both within internal, also the data which we're collecting from external. And the key is first, let's get all the data into a single place and basically make it available. And once we have a problem and try to get into this raw data format and format in such a way that this data can be used for that particular problem. So this is how we have been trying to solve our problems within GE Aviation. And based on my experience of in this space for a little more than a decade, I can tell, I'm sure if each one of you will relate to that. The challenge is not building models. The challenge is to getting access to the right information, right data sources. And that is 80% of the time when you want to build predictive models. The remaining piece is I don't want to trivialize, but once you have the right data in a format, your job becomes much simpler. So not especially for a upcoming data scientist and machine learning enthusiast, I want you to be aware that there is a lot of work which needs to be done upstream with this data. And once you have that, then you can build good models. If you don't have that taken care, you are going to be in some shape and form problem going forward. Now, whatever I have discussed, if you don't have a conversation about like whatever we are doing, how does it matter to customer? Why they should care about this? Especially by putting the predictive analytics and analytics-based maintenance solution, which gets powered by variant data sources, both coming internally and externally. we are able to make a significant differentiation for our customers. In this case, what I'm showing is a customer outcomes from a Middle East operator who is one of GE Aviation's biggest customer. And these are the numbers which are quoted by the operator directly. As per them, because of the way how we implemented some of these advanced predictive maintenance solutions, they were able to reduce their disruptions by more than 56%. They reduced their overhauls by 15%. And very important is they could get additional 12 days of utilization, which is extremely, extremely important for an airline because they measure their efficiency on how efficiently they are using their asset and what is the asset utilization, because that's the most costliest asset what they have, and it is supposed to fly. And if it is sitting idle on the ground, they're not making money. So because of these advanced solutions powered by varying data sources, we are able to make significant outcomes and influence customers in a very positive way. And I want to conclude the conversation, especially with respect to our lessons learned. Because as you can imagine, especially this area of machine learning, artificial intelligence, data science, it has become very commonly used word, which is a good news, bad news, because sometimes it gets used without being fully understood. At the same time, you need to have underlying systems to put your advanced solutions in production. So what I'm going to talk about is GE Aviation's lessons learned for the past a little more than 10 years on what is that we learned in this journey. And again, I repeat, this is not that these are the only things which you should care, but this is just some of the things which we learned. Especially when you're trying to put a machine learning based solution into production, you clearly need to understand what type of problems you're trying to solve. These solutions may not solve everything for you, but it will solve some of your problems. Again, when you have this analytics, how do you move them into production? You need to have a very clear understanding whether you are going to make this analytics more online or offline. Online is in our aviation space. Online is as soon as the data gets transmitted from the aircraft, you run the analytic. Offline is I don't have to run for every flight every second. I can wait for say 1 week and let the data get accumulated. I can run all that 1 week worth operations in a single analytic. Basically, whether it's online or offline, the type of problem decides where you have to go for that. But the type of analytic, whether it's online or offline, decides the platform, how you want to structure your underlying infrastructure. Very important thing is these analytics, like any other thing, degrade over time just because of the way how customers might be operating, or there may be some new failure mode which is popping up which you don't understand. So you need to have a system of continuously monitoring what is the performance of your analytic once you put in production. Now, things to consider, especially if you're trying to make these models to production, what is the availability of these data sources in production? The quick example is like we know that we solved the component problem where it was failing prematurely. And we did that initially by just looking into third-party data sources and building those models in our laptop. And we know that we have now solution. Now I cannot put that solution in the production because I don't have the data source captured as within GE Aviation's production data sources. So we have to work with multiple stakeholders, both internal and external, and have pipelines established to have the data coming in a structured way into GE Aviation's lake. That brings another next point. What is the technology sync up between your POC and production systems? And the last thing, which is extremely important, what is the right balance of the team? Like when you're trying to solve problems like this, you need to have people from data scientists, software engineers, subject matter expert, or business owner. That basically summarizes by below graphic. You can have a significant outcomes for your customers in the predictive maintenance world. It could be improved asset reliability, planned versus unplanned maintenance, reduce the inspection burden, and also improve efficiency at every angle. Now, how we are able to do that? The key is get the data automated, continuous, and curated flowing into your production system. Very important thing is you cannot have this problem solved without having a very good mix of domain experience, because domain experience guides the artificial intelligence side of it to know exactly what we have to look. Otherwise, as I said, these are class imbalance problem. You just blindly apply some of the machine learning techniques, you end up with false positives. The key is get the right data, coupled with the domain experience, and coupled with the right machine learning experience. That's when you start making differentiated outcome for customer. With that, I open it for any questions you may have on how we are actually advancing this journey within GE Aviation.
Very good, thank you. We have our first question. Do you have a central team that brings your data into the data lake?
Yes, we have a central team for the entire GE Aviation team, GE Aviation franchise, which works across the enterprise to capture the data sources internally. And the same team works with the external sources to pull all the data sources together into lake. It's a centralized team across GE Aviation.
Okay. Related, does all your data come from your data lake, and is it automated, continuous, and curated? If not, which data is hardest to get to?
Not all data, as I said, we try to get as much as possible all the data sources into the lake. Again, I'll go back to this slide.
I'm sorry, Dinakar, I had to stop your slide share in case you wanted to put your camera on, so I apologize for that.
Can we get back to it?
Yeah, you'll have to reshare, I'm sorry.
That's fine. I think I can speak without a slide. That's totally. What I was referring to was I had a slide how we are bringing the data into the lake. So we try to get as much as both structured or unstructured data in the raw format, and try to kind of like stitch them together to build some of these models. Now, what is easy versus what is a little bit complex is whatever we are getting from sensor side of it. Sensor data is a little bit easy to work from a structure perspective. But if I want to couple that with some of the unstructured data, for example, like the logs written by customer, the logs written by our field people, how do I really curate that data and link it to asset and make in the Carfax equivalent version of that? Getting that unstructured data linked is sometimes good, sometimes is challenging.
Okay, can you turn your camera back on? There we go. I have a question. The number of customers that you have to deal with and the customization of dealing with each, how do you handle that?
It's an excellent question. What we try to do is, initially we try to build some of these models at an overall fleet level. For example, like if I'm operating let's assume GE90, which is our big, large commercial engine, which if you're flying from say Middle East to US, typically you're powered by that engine. Now, what we try to do is we try to put a model which is at an overall fleet level, but sometimes if the model performance is really great and it's working well for one customer, it's not working well for another customer, we try to kind of like build a model which is very customer centric. So it's a mix of both. In some cases, we have a fleet model and the data gets fed and the output comes from there. In some cases, we build a model which is very, very customer specific. Just that could be potentially coming because of configuration and some other aspects, but we take a blended approach to solve the problem.
What role do you and your team play in helping your customers adjust to your recommendations?
Actually, as I said, I lead the data sciences and analytics function within GE Aviation. My team's responsibility is to technically put these models and help customers to understand what output we are getting from these models and articulate the story back to customers saying that like this is why we are seeing what we are seeing and this is the reason for that. And of course, we partner heavily with the domain experts and the commercial teams to tell the story. Very important thing is customers want to, they love the output, but at the same time, they also want to understand why the output is being driven the way how it is driven. So important is many of the artificial intelligence models are black box models. So my team's responsibility is to put a system or put a framework in such a way that we are able to clearly articulate the customer problem, what we are trying to solve, how we are able to build these contemporary models, and how it can help them going forward. And we also, that's from an external perspective. And when it comes to the internal within GE Aviation, my team partners with the subject matter experts and the central data team to coordinate what data sources we may be needing to solve a particular problem on a given day.
Well, thank you. Those are all the questions that we have. Do you have any final thoughts you'd like to share for other people who are striving to achieve what you are doing at GE?
As I said, Peter, earlier, I think this is a journey. And especially my sincere recommendation is you need to have a problem to apply technology. Don't try to put the technology before you know what problem you're trying to solve, number one. Number two, when you're doing exploration, it's fine to look into all the possible data sources. But if you want to take something into production, start thinking about that step before you really go to your final finish line. Because other times you go to the finish line, then you realize, oh shit, I don't have the right data sources to put this in production. So when you are in the exploration phase itself, once you initially start getting some encouraging results, start thinking about whether am I going to mimic this? Can I repeat this in a production system? And the third piece, very important, is just make sure that you have the right mix of a team. As I say, this area is a team sport. It is not going to just be successful only if you have data. This is not going to be successful if you have only subject matter experts. This is not going to be successful if you just have only machine learning experts. It's a combination of these three coupled with the right infrastructure is what is going to make a differentiated outcome. So that's how I summarize it.
Nice. A question just came in. Do you plan to open up your data to external companies?
At this point of time, this is mainly for GE Aviation internal use, and we actually share some of this information with our customer, but that has to be our customer.
Okay. Well, listen, thank you so much for joining us. This has been an invaluable sharing of information. And I believe that if anybody needs to get in touch with you, they can contact you on LinkedIn, or where's the best place?
I think LinkedIn is perfectly fine. And I have given my email address in the presentation, and that's already there. So LinkedIn, email, both works for me.
Great. Thank you again so much for your time. Take care.